This video is a review of the content covered in the video entitled Observers and the Orthonormal Basis. It deals with the relationship between coordinate and orthonormal bases and includes some extra material and an extra example. So the components of a tensor, such as a vector, in an observer's orthonormal basis represent measurable physical quantities. So for example, an observer in Minkowski space-time using the standard orthonormal basis here can express the momentum of an object with the four vector in terms of this orthonormal basis components and orthonormal basis vectors. Now the energy and the three momentum components of this object are given by, the energy is pt hat, this is in the orthonormal basis, the time component, and the spatial components here. Now in this space-time, an orthonormal basis satisfies the condition E alpha hat, E beta hat, little hats representing orthonormal basis vectors and components. And eta alpha beta hat is the flat Minkowski space-time metric here, with the diagonals all 1 and the time component diagonal being -1. And just in relation, for the basis vectors for the time component in the time direction, E0 hat dot E1 hat, E0 hat here is -1. All right, now, in special relativity, observations are made by observers at rest in an inertial frame and with respect to the axes of that frame. Just as in this diagram here, the axes here are made with respect to the corners of the laboratory, where the walls join, and the clock. An observer in space-time can be thought of as contained within a small laboratory that moves along a time-like world line. For our metric signature being used here is ds squared less than 0. And here's our observer at rest with respect to the laboratory. Now, observations are made with respect to the axes here of the laboratory and the clock of this laboratory. And together they form an orthonormal basis in which the observer is at rest, so the observer's own orthonormal basis. Right, now the clock at rest in this laboratory defines a time direction that is related to the four velocity vector of the observer, so we'll have a look at that. But here's the world line of the laboratory, all right, and the axes we saw earlier, E1, E2, and then E3 is suppressed in the Z direction for obvious reasons. And here is the time component, the time axis, the basis vector in the time direction, which is tangent to the world line. Now the four velocity of an observer in the laboratory is 1 on C, the scaling factor 1 on C, you'll see why shortly. The four velocity of the observer is given by this object here in the parentheses, and you'll see why we need the 1 on C shortly. All right, and so here's our four velocity here of the observer in the laboratory, and at rest with respect to the laboratory, so it's the four velocity of the laboratory as well. And we see that the spatial components of the observer is at rest within the laboratory, and so these spatial components will drop to 0. And we're left with just this bit here. Gamma is equal to 1 because the observer is at rest with respect to the laboratory and so not moving, so gamma is 1. And we have just the time basis vector here. We have the C here, which is now factored out by the 1 on C factor out front here. So cancelled out by the 1 on C here, and we're left with just the basis vector in the time direction. So that becomes, for the observer at rest in the laboratory, that becomes their four velocity. So the time direction defines their four velocity. Now if the laboratory is at rest in some inertial frame, then its axes will also align with those of that inertial frame itself. So they don't have to align in the graph here, they don't have to align with these axes. They can be quite independent of them unless they're at rest with respect to some inertial frame. All right, now in curved space, we have our manifold, and for instance here we have a two-dimensional manifold, and we have the coordinate curves where one coordinate's held constant and the other is varied. And so we generate this set of curves and they define our manifold. The basis vectors are built from the coordinates that define the manifold M, and as a result they are called the coordinate basis, and they vary from point to point on M. And so also it turns out also the orthonormal basis will vary from point to point. But you'll see an orthonormal basis will be a unit magnitude and all the vectors perpendicular to each other, but we'll get to that shortly with an example. We better look at that in an example. Now, an event P on this manifold, at some point P, vectors to that point in that point are tangent, live in the tangent space to that point. And the tangents, there's a different tangent space for each point on the manifold. So you can't compare vectors from point to point because they all lie in a different tangent space. They each have their own, in this case, a tangent plane because the manifold is two-dimensional. So they have their own plane. At each point P on this manifold, it's a different plane. So we can't just add or subtract vectors or compare them because they're different from point to point. All right. Now, next bit. Now, the equivalence principle tells us that in a freely falling, non-rotating laboratory that is occupying a small region of space-time, so a laboratory the size of the Hubble Space Telescope or the space station or what have you, is small relative to the overall size, say, of the Earth. And the Earth is only a small astrophysical object anyway. So for a small region of space-time, then the equivalence principle tells us that, provided there's no rotation, is that our laboratory, the laws of special physics are those of special relativity within that small volume of space-time. And what that means is that any point P in space-time has a neighbourhood that is homeomorphic to, and well, the reason for the application of the laws of special relativity is that if you, in a curved space, you pick any point P, then local to that point, and that's a small surrounding neighbourhood, so local to that point, that space will be homeomorphic to a Euclidean space of the same dimension. There's a whole video of this on manifolds and tangent space and all the rest of it, so on this channel, so have a look at that. Now that means we can find local coordinates at P that transforms the metric G alpha beta into the flat space Minkowski metric eta alpha beta. Now if we just stop there for a moment, if you just think of the surface of the Earth, looking at it from space, from the space station, the Earth is clearly curved, very curved. It's almost spherical, almost a perfect sphere. But if you go down onto the surface of the Earth to your neighbourhood and you look around your neighbourhood, the Earth appears very flat for a number of kilometres out. I mean, you drive to your local shopping centre or to your local shops or down the road somewhere, it all appears very flat around you. And it's only because at any point on the surface of the Earth, local to that point, it appears homeomorphic to Euclidean space of the same dimension, in this case 3 dimensions. And that's the point here. Over a small region, curvature appears to have disappeared. It appears to have been transformed out and becomes flat, but only for a small region around that point. Zoom off out of the Earth, and you start to notice the full curvature again. So local to some point P on the Earth, everything appears flat. So at some point P, the metric G alpha beta at that point P simply becomes the flat space. There are a suitable set of coordinates that you can express P in, and that gives you the flat space metric eta alpha beta. And another way of looking at that is that the partial derivative of the metric with respect to the coordinates that make up our manifold at the point P are 0. And so because this metric here, eta alpha beta, has all constant components, so its derivative will be 0. All right, so with the help of the equivalence principle, we can see that for our observer in laboratory, in curved space-time, in that small region of that laboratory and the small area surrounding it, provided it's not too great, the small region surrounding that laboratory, the laws of special relativity are an excellent application, are highly applicable, and are very good for describing that region. All right, but only for a small local region. All right, globally, the space is curved, very curved in the case of a sphere, but locally it appears flat. And so thanks to the equivalence principle, locally we can say the laws of special relativity apply. All right, so what we have so far is we've discovered that there are 2 bases. There is a coordinate basis and an orthonormal basis. So just to see how the difference between the two, let's just use a simple example of plane polar coordinates. So x1, x2, our coordinates, plane polar coordinates, x1 we're going to transform to rho phi, and the transformation is in the form x equals rho cos phi and y equals rho sin phi. And we're going to look at generating a coordinate basis, and then we'll look from there how to generate an orthonormal basis. All right, now using the position vector in flat space, we'll generate the coordinate curves for our manifold. So here's our position vector in Euclidean space. Here it is. Transform now to plane polar coordinates, and now each of the coordinate basis vectors are found. E1 or E rho in the rho direction is dr E rho, and E2 or E phi, that's in the phi direction, the angular direction, dr d phi will be, this partial derivative will give us a second basis vector. Now this is the coordinate basis vectors that we're about to find. So here we go, E rho is dr d rho is d rho of this object, which gives us this. E phi, dr d phi is d phi of this object again. Here we are, the position vector. And when we differentiate that with respect to phi, we get this object here. Now the magnitude of these vectors in general for a coordinate basis are not 1, and sometimes 2, they may not even be orthogonal to each other. So the magnitude of the basis vector, coordinate basis vector in the rho direction is this object here, which is 1, so that's nice. In the phi direction, it's this object here, which is not 1. Now these vectors form a coordinate basis, with the coordinate basis vectors satisfying the following condition, and it's this condition I'm about to show you that will tell you you are in a coordinate basis. All right, so E alpha dot E beta is G alpha beta, the metric for that space. So for plane polar coordinates, here's how we find our metric. G rho rho, G phi phi, and then these two here will be 0 because the scalar product of R phi rho E phi E rho will be 0. They're orthogonal to each other, so the off-diagonal terms here will drop out, will be 0. But G rho rho is 1 as we just found, and G phi phi is rho squared. All right. So in our example here, we can form an orthonormal basis from our coordinate basis in the form E rho hat and E phi hat. This will be our orthonormal basis, 2 vectors in it for this two-dimensional space. We'll have E rho, 1 on rho, E phi. There's, in terms of the coordinate basis, E phi, if we multiply that by 1 on rho, we get an object E phi hat, which is now also an orthonormal vector, orthonormal basis vector, and E rho, which as we found is the same, E rho hats are the same as E rho. Both have magnitude 1. Now once again, the orthonormal basis vectors satisfy the condition E alpha hat plus E beta hat is 1, 0, 0, 1. All right, so in Minkowski space, this top one will be -1, but in general in flat space, we have this diagonal with the 1s in it and everything else is 0. So a coordinate basis satisfies this, and in space-time, an orthonormal basis will satisfy this is equal to the flat Minkowski metric. But in this case, it's just equal to this 1, 1 here for polar coordinates for our example. All right, any vector in curved space can be expanded in, and not just curved space, but can be expanded in the coordinate basis and these coordinate basis components, or it can be expanded in the orthonormal basis with this orthonormal basis components. So coordinate basis components, orthonormal basis components, all right, coordinate basis vectors, and orthonormal basis vectors. All right. Now this suggests that the components of these vectors can be related. So we've got some vector v phi, e phi in the coordinate basis is 1 times e phi. Now we know from previously that if we just do rho times e phi hat, you'll get e phi. Because remember, e phi hat had the 1 on rho times e phi. So by definition then, this must be equal to this, and then this must be equal to e phi hat, because remember this and this must be equal to this, because you can expand it in either basis. All right, so v phi, v contravariant phi up here, the coordinate basis component is 1. We chose the problem to be that that case, 1 times E phi, and that's equal to rho times 1 on rho, and that gives us, which is equal to, because the way you can get 1 is times rho by 1 on rho, so the rows cancel and you get 1, so that's the only way you're going to do that. Now this 1 on rho happened to be the alpha component, if you like, or the orthonormal basis component, which we use this parentheses to describe this object, and we'll look at this in more detail shortly, but this object times the orthonormal basis component, E phi hat, which is rho, all right, times this object here gives us 1. So there's a relationship between the coordinate basis component here and the orthonormal basis components here. All right, now, how do we read this? So E1 hat in parentheses with a 3 up means the 3 component of the vector E, of the orthonormal basis vector E1 hat. E3 1 hat means the 1 hat, or the first orthonormal component of the vector, of the coordinate basis vector E3. All right, and the components are related according to, as we've already discovered, this first one here, the coordinate basis component is equal to this, and the orthonormal basis component is equal to the coordinate basis component times the B hat orthonormal component of the coordinate basis vector here. Now, on the previous video that this video is summarizing, I went into more detail with some examples about that, but I won't go into that again. You can have a look there for that. Okay, now just in general, for a diagonal metric on some pseudo-Riemannian n-dimensional space-time manifold, then a suitable orthonormal basis is given by, just here its components, but the components in the orthonormal basis E0 hat alpha is this one here. The next component, 1 alpha, is this object here, and so on down to the nth component. Right, nth basis vector component. Remember, the parentheses mean that they are the component of the basis vector. In 4-dimensional space-time, you're going to have a time component, the first spatial component, the second spatial component, and then the third spatial component. So in 4-dimensional, you have 4 of these coordinate components here, orthonormal basis components, here. But in n-dimensional space, you can go all the way up to n. But here's the general rule given some pseudo-Riemannian n-dimensional space-time manifold. Here are the components. Next, note also the relationship between the reciprocals of these coefficients. So if you wanted to find, if you now have the alpha hat up here and the coordinate component thing down here, then this is the same as 1 over. They're just reciprocals of each other. And so E upper 1 hat 1, the first component of the orthonormal basis component, then you have 1 over this object here. So that's 1 over 1 on the square root of G11, which is just the square root of G11. So it just depends on what you're in. Okay, as a general rule now, and we're going to have a look at this in more detail with some examples, and you've also seen in the previous video to this one, which is called the observer and the orthonormal observers and the orthonormal basis. So have a look at that video as well in conjunction with this video, put them two together. Now the relationship between a tensor T and the coordinate basis and its orthonormal basis T hat. Remember, we often want the orthonormal basis because that's the basis in which we perform measurements, and its components represent physically measurable quantities. So we often want to convert to the orthonormal basis when we want to talk about measurements, or if we want to make a prediction of what those measurements will be, we need to do so in the orthonormal basis. Even though we often, most of the time, work in general relativity in the coordinate basis, we often, our tensor T and the coordinate basis, we sometimes do need, as you'll see in the following examples, to go to the orthonormal basis when we're going to make a prediction about what will be observed. The components of the objects in an orthonormal basis will be physically measurable quantities, as you'll see shortly. So here's our tensor. This is in the mixed tensor of rank P, contravariant P and covariant Q. In the coordinate basis, this object here, if we want to transform it to the orthonormal basis, because we may need to make some predictions about what we are going to observe, then we need to multiply by each of these coordinate components, coordinate basis components. Okay, so for the upper ones, alpha 1, alpha 2, alpha p. We multiply by these objects here. Remember, that's this reciprocal thing here, which is just 1 over these. And then for the lower components, the covariant components, beta 1, beta 2 up to beta q, we're multiplying by these all the way up to q here. And for the alphas, it went all the way up to alpha p because we've got alpha p here. All right. So inside the parentheses are the orthonormal components, and then the alpha out here and the beta out here represent the number which particular component we're after. Let's go. So once we're in the orthonormal basis, we then can calculate the Ricci tensor and scalar if we have the Riemann curvature tensor. So if we, from the Riemann curvature tensor, we want to get, sorry, this gamma here should be lower. It actually should be in the subscript form here. Sorry about that. So it should actually be here. My apologies. It should be, it's one of the components, one of the indices, sorry. It's one of the indices and it should be down here. Sorry about that. So if we want to get the Ricci tensor in the orthonormal basis here, we've multiplied by the inverse Minkowski metric, both indices raised here, and that will then sum out the delta here and the gamma here, and we'll be left with our Ricci tensor with the alpha hat, beta hat components. So that's in the orthonormal basis. The Ricci scalar, same way again, the inverse Minkowski metric here, multiplied by the Ricci tensor in the orthonormal basis here. Notice the hats here for the orthonormal basis. That gives us the Ricci scalar. Now, calculations are often carried out in the coordinate basis because they're easy to calculate, as the plane polar coordinates example showed. Our measurements are actually the components of some orthonormal basis. So we need to convert to the orthonormal basis, which is what I've explained on the previous page. Now, in the first video in the series on Schwarzschild geodesics, we're going to look at an example now. The acceleration of a massive object in the radial direction in a Schwarzschild space-time is given by, we found it to be this object here. So the acceleration in the radial direction towards the Schwarzschild mass was here. Note that this is in the coordinate basis. And the net force on this massive object of mass m in this base, so there's a massive m, maybe it's our laboratory accelerating towards the Schwarzschild mass. And we want to know the net force on it. Okay, well, in the coordinate basis, we end up with this very Newtonian looking object. Fr here is the mass of the, say, our laboratory, times this is minus m times negative because it's inward, in the inward direction. Now, the actual force measured by the observer is that which is measured in the observer's own orthonormal basis frame. So here we go. Here's our observer inside the laboratory, accelerating towards the Schwarzschild mass, and they have their own reference frame inside the laboratory, their own orthonormal basis. They have the corners of the room acting as the corners of the laboratory acting as their axes, and they wish to make their measurements against that orthonormal frame. Well, to do that, we need to go from the coordinate basis, coordinate frame Fr here, to the orthonormal frame, orthonormal basis frame Fr hat. Now, there's only one coordinate to deal with here, it's the radial coordinate, and so we need to multiply by this object here. Notice the R up, the R down, and the R hats are up, they match in the same position here. So we need to multiply by this component to transform this into what would be measured by the observer inside the laboratory. So if the observer has their own little force meter, or if the observer has its own motor, for instance, and needs to provide a force, needs to provide a thrust force, how much would it be? Well, what we will actually measure is not Fr, but it's Fr hat is what the observer in that laboratory will measure. So they need Fr hat because that's what they actually measure. All right, now just notice here, just reminding again, ER hat up with the R down is 1 on this, is 1 over 1 on that, which is this object here. If you look at the Schwarzschild metric, you'll see that the radial part coordinate, the GRR, was this object here. And so, well, the square root of GRR is -½ here, but in the Schwarzschild frame, GRR is +1 up here. All right, now let's say this object is the observer's own laboratory, and so the observer measures a force acting on his or her laboratory to be FR hat in their own orthonormal basis frame. They measure this, they don't measure this. And so let's multiply this by what we had before. So what we had before was this bit here, minus mgm on r squared, and then we're going to multiply by this object here, which is this. And when we do that, we produce this object here. Now this is larger than the Newtonian value. Okay, so this bit here is the Newtonian part here, which is what we got from the coordinate basis, FR, but the actual measured value will be given by this. In other words, if the laboratory has its own rocket motor and it needed to provide a thrust force to keep itself at a constant radius, then it would have to be the plus of this. It would have to be equal to this, but in the opposite direction. So that would have to be a plus, and it would have to be equal to this amount, not equal to the Newtonian amount. It would have to be equal to all of this to hold itself at a constant radius. That's the amount of thrust the engine would have to provide in the orthonormal basis observer's reference frame. So the observer in the laboratory would look at his or her dial and would see a force equal to this. Their instruments would measure this, not this coordinate value we found earlier. All right, so now the other thing to note, this is larger than the Newtonian value and, interestingly, becomes infinitely large as the laboratory approaches the event horizon of our Schwarzschild black hole. As it approaches the event horizon at r equals 2gm on c squared, as it approaches that, if you put here r is 2gm on c squared, the c squareds will cancel. You have 2gm minus 2gm, this is 0. You've got this object over 0, so it becomes infinitely large as we approach this value here. So as we approach the event horizon, and you approach the amount of force required to hold at a constant radius approaches infinity, as measured by the observer in the laboratory. All right, and that's the difference here. This video is just another look at observers in a coordinate basis frame and in an orthonormal basis frame.